Hi there, my name is Fritz, and today in this video tutorial I'm going to show you how to use the LSAfun package for R, which is a package that I created some years ago and that allows you to explore distributional semantic spaces or other vector spaces using R. If you need further information on this, you can always read the paper, which is this one that appeared in Behavior Research Methods in 2015, and where you can read up everything that I'm going to talk about in this video. So if you need some written instruction, please just check this paper. It contains everything you need. Let me first briefly explain to you what distributional vectors are and what you can do with this package, because I think it's easier if you have some concept of what it is that it allows you to work with. So distributional semantic models are models of semantic representation. They are supposed to tell you what words mean. And the core idea is that a word's meaning can be approximated by its distribution in language. So the idea is that words with similar meanings tend to appear in similar contexts, whereas words with different meanings tend to occur in different contexts. So in this example, you can see that nurse and doctor, if you look at large collections of language, tend to appear in similar sentences with similar words, such as patient, medicine, hospital, whereas a word such as whale appears in very different contexts, with ocean, but not with patients, hospital, medicine. And you can, of course, just calculate the distribution of these words over these contexts. For example, here are the distributions of nurse, doctor, and whale over these 4 different context words. And you can see that those two are very similar. The distributions are very similar. So the idea is that the words are also very similar, whereas whale is not very similar to those two, which means in these rows of the matrix, you now have vectors. And if you just plot these vectors as a graph, you can see that doctor and nurse are kind of close together, whereas they are not so close to whale. You can see that the angle between those two is very small, which means that the cosine of this angle is very large. And that's the reason why cosine similarity is taken as the standard similarity measure in these distributional models. So in this case, small angle here means a high similarity between doctor and nurse, whereas large angles here and here mean that doctor, nurse on the one hand and whale on the other hand are very dissimilar. Of course, in order to work with these kind of models, you kind of need these models in the first place. So you need a corpus and you need to calculate all the distributions, and that can take a bit of time. And this is where LSAfun comes in. LSAfun offers you an interface to pre-created models and an option to use models that already exist in R. Let me show you how this works. So first thing is you need to install and load the LSAfun package. You can install any package in R by using this command, install packages, and then you just type the name of the package, LSAfun, and you run it. And it will take a bit of time because it needs to download the package, extract everything, and install it on your computer. Once it is installed, you can load the functions of the package by using the load command, load LSAfun. I'm going to let this run in the background, and in the meantime, I'm going to show you the other component that you need, which is you need some semantic space. And if you don't know how to do that yourself, or if you just don't want to do that yourself, but use something that has been empirically validated before, you can get these spaces from different sources, one possible option is to use my homepage, which means you can just go to this page, www.fritzgünther.de. It will forward you to my homepage, and here on the right-hand side, you can find software and resources, semantic spaces. This has a bit of introductory text that shows you where you can find different semantic spaces, but more importantly for our purposes now, it also provides at the bottom of the page several semantic spaces that you can download. You can see a list of currently available spaces here, and today I'm going to use this UKWAG SIBO corpus semantic space. It's not important for our purposes right now what exactly this contains. Let's just take it for granted. So I'm scrolling down. Here I can download the file. I click on download. It forwards me to a Google Drive page. Takes a bit. Let's wait a few seconds. And now I can click on download. Okay, there. I assure you that there are no viruses attached to this. And I'm going to save it in my external hard drive G in the directory demo. Just save it. Takes a few seconds to download because it's 500 megabytes. We wait for it to download, and in the meantime, we go back to R. So now I'm back in R. You can see that the thing is still being downloaded here. The next thing we need to do once we have the complete download is we need to load it into R. So the whole vector space has to be loaded as an object into R. And since on my homepage, I'm providing all these vector spaces in the RDA format, which is already the format that is native to R, so it is saved as an R data object, I can just use load and then type the path to the file that I just downloaded. So G demo ukwagsebo.rda. Will also take a few seconds, but not very long, and then it will appear here as an object in my current environment. Okay, now the package has already been installed. I'm going to load it. I noticed that I put in the wrong command here, so it's library LSAfun. I'm going to run this. It will load a few dependencies. The RGL package is quite large, so that also takes a bit of time. And now I'm ready to go. So first thing you might want to do is just check how these things look like. So what you can do is type the name of the object. You can see here that the object is called UKWAG. And in order to assess any vector, you can just type in, I don't know, let's check lion. So of this large matrix, we extract a single row, the one that has the row name lion. And you can see that it has a lot of dimensions. It's 400 different dimensions. And here you can see the dimensional values on each of these dimensions. These are essentially the equivalent to what I showed you before, the equivalent to these dimensional values here. Okay, so this object is a named matrix. You can check the dimensions of this object here. So this particular one has more than 200,000 entries, and each of them has 400 dimensions. Each entry is a row of this matrix, And you can check the words that are included in the semantic space by using row names. So here are the first 1000. So all the words serve as row names. This is the format that LSAfun needs and expects. So any semantic space you're loading needs to be a matrix or a data frame with all the objects, so all the individual rows having the same dimensionality, and with the names of these vectors being the row names of the matrix. Again, if you load any space from my homepage, that's going to be the default format you get there. Next, you might want to check which words exist in the semantic space. That's very easy. You can just do something like this: lion in row names UKWAG, and you will find that this word is included. You can also search for multiple words like lion and tiger. This means that the semantic space has a vector for lion and for tiger. But you can also insert some nonsense here, for example, bulio, and you will find that this is not a word that exists in the semantic space. Obviously, you can only perform computations for words that exist in the semantic space. What are the possible computations? There are quite a lot of them. Today, I'm going to show you the most useful, the most common ones. For a more exhaustive list, you can always check the paper. The standard operation is to compute the similarity between two words. You can do that using the cosine command with a capital C. Here you can say, okay, I want to compute the cosine between tiger and lion. And as you can already see in the proposed arguments, you also need to specify some object T vectors. T vector stands for term vectors, which means you need to specify the semantic space in which are searches for these vectors. In this case, we only have one, so T vectors is UKWAG. So in this UKWAG matrix, it will search for the rows using tiger and lion as a row name, and it will compute the cosine similarity between these two rows. In this case, it's 0.47 something. The cosine similarity always ranges between 0, which means not similar at all, and 1, which means as similar as possible. To check whether that's high or not, you can also compute the cosine between other things, for example, tiger and tulip, which is far smaller. Let's check if I can find something very similar, for example, man and woman. This is quite similar with 0.58 something. So that's how you use LSAfun to compute the similarity between any pair of words. Of course, sometimes you might want to compute the similarity between more things than just one pair of words. For example, you might have a case where, I don't know, you have a data frame called dot, which contains, let's say, a prime word. And here you can have either tiger, lion, or tulip. And this data frame also includes target words like rose, flower, and daisy. So you could have a data frame like this, where one row contains one set of words, where one column contains one set of words and the other column contains another set of words. For example, if you have any form of experimental material that you are using. And in order to compute all these pairwise similarities, so between tiger and rose, lion and flower, and tulip and daisy, you can use the pairwise function. So in this case, pairwise between dot prime and dot target. I have to specify the semantic space in which to search, which is UKWEC. And I get these 3 cosine similarity values. And of course, I can attach them to my data frame again. So that cosine is the output of this computation. And then you get this nice matrix format, which gives you always the cosine similarity between prime and the target. In some cases, you want to compute all pairwise similarities between a set of words. And this you can do with the multicos, so multiple cosines function. For example, I can say I want to compute the multiple cosine similarity between all the prime words. Again, I have to specify the semantic space. And then I get this matrix that gives me all pairwise similarities for this list of words. The default assumption is that the words in your rows are equal to the rows in your matrix. So it will just give you all the pairwise similarities. If you want to have different words in the rows and the columns, you can also specify that by saying something like, I want to compute multiple cosine similarities between all the primes on the one hand and all the targets on the other hand. And this will give you this output. So now the primes are in the rows and the targets are in your columns. Let's come to the final demonstration for today, neighborhood explorations. In this type of model, a neighbor is defined as the most similar words to a given word. So for example, if I want to compute the neighbors for lion, I have to specify how many, let's say 20. And again, T vectors is UKWEC. It has to crawl through the entire semantic space, compute all possible similarities. And at the end of this process, it filters out the most similar ones. So in this case, the most similar word to lion, except for lion itself, is dragon, followed by Androcles, followed by leopard, couchant, then here's tiger, beast, giraffe, and so on and so on. So these are the closest words to lion that you can get in this semantic space. And if you want to explore this thing visually, you can use the plot neighbors function. It should just work like this. Again, takes a bit because it has to go through the entire semantic space. And then you get an output like this. You can play around with it. It's a 3-dimensional projection of this sub part of the semantic space. And here you can see not only the word itself and its similarity to all other things, but also the similarity structure of the entire neighborhood. So words in the neighborhood that are closer together will be plotted as close to one another. And you can see that the neighborhood of lion falls into different, let's say, subclasses. Here you have different animals. Here you have more, I guess, mythical or medieval stuff. And here, I don't know, to be honest. And this might be very interesting if you have polysemous words, for example, when you check the closest words to mouse. And let's check not only the closest 20, but the closest 50. I wait for the computation to complete. And I'm sharing this neighborhood. And here you can see that mouse has this computer mouse field on the left. Here's also stuff related to computer mouse, but here you have things like rat and rodent. Okay, these are like the core functions of LSAfun. As I said, if you are interested in more functionalities, you can always check out the BRM paper. The link to the BRM paper and the link to my homepage are in the description. And I hope that this was useful to you. And thanks a lot and bye.